Tolerances. A fundamental idea in mechanical drafting is that there are no perfect parts. There are very smooth parts, nice looking parts, but if you were to look at them up close, like through a microscope, you'd see there are all kinds of bumps and valleys in them. And they're not perfectly straight and not perfectly cylindrical. It's not possible. Let's think about an example of a part that does not have a tolerance. So you've put a half-inch diameter on this pin, and the inspector out in the shop measures this part, and it's 501,000ths. Well, that's pretty close. It's only 1,000th over. Is that okay? They might call you up and ask you, what if it's 0.499, a little bit under? It's pretty close. Is that okay? You could spend all day on the phone answering questions like that. So we put tolerances on our drawing, and this tells the machinist what to make, what their goal is, and it tells the inspector which parts are acceptable and which parts they must reject. All because no machine can make perfect parts. Even though we can have very close tolerances, we cannot make perfect parts. So you specify how much variation you can tolerate by applying tolerances. A tolerance is the acceptable amount of variation, and you can write it either this way, like a plus-minus tolerance, or this way, a limits tolerance. Both these parts say exactly the same thing. Remember last time we talked about the fundamental rules, and the very first rule said each dimension shall have a tolerance? Well, there are two ways you can do that. You can apply the tolerance to the dimension, plus, minus, or limits, or you can put it in the title block. Here are plus-minus tolerances and the same part with limits tolerances. By the way, can you tell by looking at this whether this is inch or metric? I hope you are noticing that there is no leading zero, therefore this must be an inch dimension. Here's another part, two versions of the same part that say the same thing. How about this? Is this inch or metric? You can tell that this is metric because it does have a leading zero, and it does not have trailing zeros. So you put the plus tolerance on top. Here is ASME talking about this. You always put the plus, the bigger tolerance, on top, and it can be zero in one direction. It could be plus 0.1 minus nothing, or it could be nothing minus 0.3. But you have to give that zero even if it's zero. And when we go to AutoCAD, we'll see that they call this plus-minus tolerance the deviation method for some reason. You might have tolerances that are the same up and down, plus 0.2, minus 0.2. And when you have that situation, you use the plus-minus symbol and just write the tolerance once, plus or minus 0.2. AutoCAD calls this method symmetrical. If you want to use limits, they specify the maximum size and the minimum size. And here is ASME showing limits dimensions. Again, you write the big number on top, the small number on bottom. And AutoCAD calls this limits, which is what ASME calls it. You can mix plus, minus, and limits dimensions in the same drawing. That's perfectly fine. And once again, there's no, one is not better than the other. You might find it easier to write one or the other in a particular drawing. Your machinist might like one better than the other in a particular situation, so you should go ask them. but they are both equally correct. Okay, just a few random interesting things to think about with regard to tolerances. This isn't really going anywhere other than I just want you to start thinking about tolerances in the real world. So here's a pin, a 2-inch diameter pin, and a mating hole, a block with a hole. And I'm feeling pretty good because I made the hole 2 inches in diameter. Sorry, I made the pin 2 inches in diameter, and I made the hole bigger. I made it 2 inches and 5 thousandths. So that seems pretty good. The pin will go into the hole because the hole's bigger. And then, because I'm cool, I put tolerances on both those dimensions. So got a pretty good situation going on here, I think. Let's analyze what could actually happen, however. What is the smallest possible size the hole could be? So its size is 2 5 thousandths, then plus or minus 5 thousandths. So it could be 2 inches, couldn't it? Now, what is the largest possible size the pin could be? It could be 2 inches plus 5 thousandths. So its biggest size would be 2 5 thousandths. Uh-oh. So we could have a pin that's 5 thousandths bigger than the hole. Looks like this is not going to work after all. Well, let me try changing something. What if maybe I'll just leave the basic sizes the same, and I'll just narrow the tolerances. Now that might not be a good idea because that makes the part more expensive to produce. So this may not be a good solution. But let's just see what happens when I do this. Now, what is the smallest size the hole could be? 2 5 thousandths minus 2 thousandths is 2 3 thousandths. Good. And what is the largest the pin could be? 2 inches plus 2 thousandths. It could be 2 2 thousandths. All right, so now we're getting somewhere. We now have, in the worst case, a hole that is 1 thousandth bigger than the pin, 1 thousandth in diameter bigger. That'll be fine as long as nothing is bent or out of round, which takes us to geometric dimensioning and tolerancing next year. Now, another thing to think about is the idea of tolerance stack-ups, which we will look at next time when we talk about chain dimensioning and baseline dimensioning. We introduce it here. So here is a part where the tolerances are plus or minus 20 thousandths, 0.02. And so if you made the part, let's say you made each dimension the very biggest it could be, that would be no problem. But what if you used chain dimensioning? What if you had all three lands and notches dimension, they're all 3/4 of an inch, and you put the overall dimension on it? So now, according to the title block tolerances, all those dimensions have plus or minus 20 thousandths applied to them. Well, that's great, but get out your calculator maybe, or your mental math, and think about what would happen if somebody made all of these three sizes their very biggest. So they would be 0.75 plus 20 thousandths. What would that be? That would probably be 0.81. They would all add up to. Sorry, that would be 2. Oh boy, I can't do this in my head. 2.31, I think. But the overall dimension also has a tolerance on it, and according to the title block, it can only be a total of 2 1/4 plus or minus 0.02. So it can only be a maximum of 2.27, but yet if you stack all these up, you'll get 2.31. So we have some conflict there. This just cannot add up, and there's a good chance of making a wrong part. So that's why we dimension our part as we see in the upper left corner without duplicate dimensions. And if we want to include all the dimensions, we make one of them a reference. A couple of other random things. This takes us to next year and geometric stuff. When we put a size tolerance on, we are actually allowing the surface of the part to land anywhere within that tolerance zone, which is interesting. And if we put a tolerance on a radius dimension, what is actually happening is if the radius is smaller, it's more pointy, and if the radius is bigger, it's more flat. So that's interesting to think about. I'm not going anywhere with that either. I just want us to start thinking about shapes. All right, let's look at the part we're going to draw for this assignment. Here are 3 dimensions that don't have tolerances, so they'll pick up the title block tolerance, and then 2 that have plus and minus tolerances. What that means is that you are going to need 3 dimension styles. 1 dimension style for the standard dimensions, 1 for the plus 5 minus nothing, and 1 for the plus nothing minus 2. And in the next video, we'll go into AutoCAD and look at how to do that. Here are some words for you in case you just need to come back and remind yourself. You'll need to set a new dimension style, and then you'll go to the Tolerances tab and select the method. Deviation means plus minus. You'll set the precision, 3 decimal places. You'll set the upper value is the plus, the lower value is the minus. So if you're doing plus 10 minus nothing, here's what it looks like. And in these values, you don't need to worry about how many zeros there are here because you have already set the precision at 3 decimal places. So it will just ignore the extra zeros. And then, this is very important, at the bottom, there's this box that says zero suppression. We need to check the one that says leading. So we are going to suppress the leading 0. If you don't check that box, your dimension will come out with a leading 0, and then I'll complain. Then you'll add a note in the lower left corner of the title block, FAO, blah, blah, blah. This stands for Finish All Over 63 micro inches. That's 63 millionths of an inch. That's the smoothness of the surface finish. This is a small part. It's only 1 11/16 long. So I recommend that you scale your viewport double size. Make your viewport 2:1. Now that is going to affect your drawing scale factor. Up to now, we've been looking at viewports that are 1:1 or 1:2. What if your viewport is 2:1? Your drawing scale factor is going to be 1/2, which I have written at the bottom of this slide. If your plot scale, if your viewport scale is 2:1, your drawing scale factor is 1/2. And if you decide to make your viewport 4:1, your drawing scale factor is 1/4. So we'll try to look at that as we look at AutoCAD.